I welcome all of you to the class. Today we are starting with lecture number 3. Today we are starting with lecture 3, and we are dealing with the concept of stress. We are dealing with the concept of stress. As far as the previous class is concerned, in the previous class we talked about the definition of a stress. So whenever you have a machine element, any machine element of any cross section, say for example its cross sectional area is A, it's subjected to force, say for example force F. Okay, then we have defined stress on the area as F by A. Fine. And in the last class we also discussed that in order to denote the stress on an area, we must know the force, that is we must know the magnitude and direction of force. Okay, and we must know the area over which the force is acting. Fine. And as far as area is concerned, we must know the magnitude of the area. We must know the magnitude of the area, and we must also know the direction or unit normal to the area. Unit normal to the area. These two things should be known to us. Fine. So this was what we had discussed previously. And if we recall, in the previous class, when we were talking about the stress on the machine element, say for example, as the example given above, we are having an area A, the magnitude of this area is A. So first of all, what we do, we will draw a unit normal. The unit normal to this area will be in this direction, and we draw this as neta cap or n cap. Now the question is, the unit normal to the area can also be in this direction. But I told you previous time that the sign convention that we have to follow is the unit normal to an area is to be drawn in such a way that if you imagine that you are having a screw, if you imagine that you are having a screw on this area, the screw is to be the torque is to be applied on the screw in such a way that its motion should be along the direction of the unit normal. Okay, so the screw on the area should come out. Okay, so if you have a screw in this area and you try to get the screw, loosen the screw, you try to get the screw out, the screw has to move in this direction, so this has to be the direction of the unit normal. Fine. So number two is the force. The force acting is also in this direction. Okay, so the force is acting in this direction, so magnitude of the force is F. Okay, and right, this is F vector. Okay, and if you say this is your I cap, and if you say this is your J cap, okay, then we define stress on area A. Stress on area A is equal force acting on an area, force acting on an area whose unit vector is along neta cap, and you see this neta cap is coinciding with I cap, a unit vector drawn along x-axis. So we write it's force F acting on an area having magnitude A and acting in and having unit normal along x-axis, that is I cap, divided by the magnitude of area, that is A. Fine. Okay. Now this is force, this is a vector quantity. So as far as this force is concerned, this force acts on an area A having unit vector drawn along x-axis, and we can also write this as, this can also be written as, force can be written as magnitude of force F. This force is acting along I cap, Fi cap is acting on an area A whose unit vector is also along x-axis, divided by the magnitude of A. So now you see you are having two vectors. You are having I cap one vector, I cap another vector. So you are having the stress depends upon in order to define stress on an area, okay, in the formula of the stress, you require two vectors. You require one vector which is associated with the force, and another vector which is required, which is associated with the area. Fine. Then this physical quantity, which depends upon two vectors, whose representation depends upon the two vectors, we said this is not a vector, this is a tensor. Okay. So it depends upon the magnitude of a physical quantity and the two directions. We'll be discussing tensors later on in broad detail. But here, what's very important for us is to understand that the representation of stress on an area requires two vectors. Fine. Then we discussed two types of stresses. We talked about the normal stress and the shear stress. Fine. As far as the normal stress is concerned, here you see in this case, the force is acting in a direction parallel to that of the area vector. The force vector and the area vector are parallel to each other. When force acts on a rigid body in such a way that it's parallel, it coincides with the area vector, then the stress generated by the force is called normal stress, which we represented by sigma. Fine. That is, when force acts on a rigid body, when force vector, when F vector is parallel to the area vector, when F vector is parallel to the area vector, then we say that this stress created by force F is called the normal stress. Let me repeat. When force F is parallel to the area vector, then the stress created by force F is represented by sigma and it's called the normal stress. This is called normal stress. So as far as the normal stress is concerned, in normal stress, the force vector, like let's say the force vector is parallel to the area vector. Your area vector is also in the same direction. Okay, your area vector is also in the same direction. So force vector and area vectors are in the same direction. The stress created by the force on the area is called the normal stress, number one. Okay, normal we often discuss as perpendicular. If you talk in terms of the magnitude only, then you see the angle between the force and area only, not area vector. You have an area like this, okay? So on this area, the force is perpendicular. If you talk in terms of scalar, if you talk only in terms of scalar, then force vector is perpendicular to the area, but force vector is parallel to the area vector. That's what we are defining. Fine. After this, we discuss the second type of stress, what we call as the shear stress. Okay. So as far as the shear stress is concerned, shear stress was defined as the stress. Say, for example, you have the same. You take the same example of the same rigid body. Okay. Its area is A. So area vector, when you draw, the area vector is drawn in this direction. I will write this as A vector, area vector. Magnitude of A and a unit vector drawn in this direction. Let's suppose the force F is now acting in this direction. The force is acting in this direction, force F. Okay, force vector. Now, if you look, if you say the force vector is, let me define this to be our x-axis, and let me define this to be our y-axis. Let me, this will be written as j cap. Then area is along x-axis and force is along y-axis. Fine. Then we define the stress as, stress is defined here in the form of tau. Here normal stress is defined by sigma. Okay, when you have force vector parallel to area vector. But here force vector and area vector are not parallel, but force vector and area vector are perpendicular. Then the stress is called the shear stress. Okay, this is called shear stress and is represented by tau. Okay, and we define the shear stress tau as, this is same force F acting on an area vector A, magnitude A. Area vector is along I cap divided by the magnitude of the area, that is A. Fine. So this is how this area is defined. Okay, so I was talking about the shear stress. Shear stress is F by A. So as far as this F is concerned, this F is acting on an area A. whose magnitude is A and is along I cap x-axis divided by magnitude of A. Now this force and the area vector are perpendicular to each other. Therefore, the stress that is called the shear stress. This is what we had discussed previous time. Now, as we move forward, we had also discussed the stress also depends upon the area of inclination. That is, I mean to say, last time we had taken an inclined area, this slanted area, okay, and we had assumed the force F acting on this area, that is F, fine. And first of all, if we are asked to calculate the stress acting on this area, okay, we know we had run a perpendicular area here. This area is A, and this area we are assuming to be A prime or A naught. Let me call this as A naught, okay. Then the force F was resolved into two. First of all, this area we have to calculate the stress. We had to calculate the stress on this area. Okay, draw perpendicular to this unit normal to this area. So unit normal to the area will be in this direction. That's what we call as n cap. Unit normal along this direction. Right. And we had assumed that this angle is theta previously, and we had also stated that this angle will also be theta. We had discussed that this in the previous class, and we had said cos of angle theta is equal uh, a by a naught. This is what we had done last time. And this f was also resolved into two components. Okay, the two components of f will be one component of f is in this direction. That's what we call f cos theta. And another component of f is in this direction. That is f sine of theta. Fine. And we had said that this f cos of theta is this component of the force, okay, which is in the same direction as the area vector. F cos theta coincides with the n vector. N vector is a unit vector which represents the area vector. If we have to calculate the area vector, it will be area of the slanted area, that is a naught. A naught vector we can write as magnitude of a naught and its unit direction, that is n cap. Fine. Now uh, this area vector is along neta cap, n cap, fine. And f cos theta is also in the same direction. Therefore, by the definition of normal stress will be f cos theta divided by f cos theta divided by the area, that was a naught, fine. And we know that is f cos theta divided by a naught, that is a by cos theta. This will be cos square theta, fine. This is what we had done last time, and we can write this as we had written this as, this can also be written as normal stress on this area will be f by a cos square theta is 1 by 2 1 plus cos 2 theta divided by 2. This is what we had done previously, and we had also calculated the value of the shear stress on this inclined area. Tau is equal to the component of the force which is parallel to the area, that is f sine theta. Okay, since f sine theta and area vector are perpendicular to each other, fine, then f sine theta on area a naught will create the shear stress, that is f sine theta divided by the area, that is a naught, that is equal f sine theta divided by a naught, that is a by cos theta. So it is a by cos theta will be f sine theta cos theta, and we had multiplied and divided by 2. Therefore, tau becomes equal f by 2 times a twice sine theta cos theta is sine 2 theta. Fine. This is the definition of the normal stress, and this is the definition of shear stress. Fine. So what I will write it here. The value of sigma, the normal stress, is f by 2a and 1 plus cos 2 theta. Okay. And the value of tau is on inclined area is f by 2a F by 2a and sine 2 theta. Fine. Let me pick up few cases to see how it matches with what we have done previously. Clearing few. Let me clear the space. I will write it for when theta is equal when theta is equal 0. That is when theta equal to 0. Look here, this is theta. When theta is equal to 0. When theta equal to 0, it means at that time the area, when theta is equal to 0, at that time the area vector and the force vector coincide with each other. That is when theta is equal to 0, we draw the figure for theta equal to 0. At that time, our area vector and force vector will coincide. Okay, so our area vector will be like this. Our area vector, unit vector for area will be like this. And our force vector will also be in the same direction, F. Fine. How we approach it, how we are drawing this diagram here, it's from this diagram. Okay, it's from this diagram. I will draw it from here. It's from this diagram, because when we say theta is equal to 0, when theta is equal to 0, when theta will be equal to 0, you rotate this n vector, then n vector and f vector will coincide. You will get a diagram like this. Fine. So when this is the case, this is your area. Fine. And you see what will happen when you rotate this n vector. Fine. Your n vector, area vector and force vector will coincide. Fine. And the area vector is in this direction now. Fine. That is what I am drawing here. Okay. So at that time, what will be normal stress? Sigma will be equal. So we'll be putting theta equal 0. When theta equal to 0, so it is cos 0. Cos 0 is 1. 1 plus 1 is 2. 2 and 2 will cancel. So normal stress will be F by A. So on this area, the normal stress is F by A. So what will be shear stress then? Tau will be equal. We have theta equal to 0. Sine 0 is 0. Therefore, tau becomes equal 0. So on this area, so when you have a case like this, so when we have a case like this, okay, so we can directly say if we have a rigid body, an area which is force is acting F, if on this area force F is acting in this direction, in the same direction as your unit area vector, then on this face there will be only normal stress. There will be only normal stress, no shear stress. There will be no shear stress. No shear stress. Fine. Now let's go to example 2, case 2, I should say. Wherein we say when theta equal, when theta is equal 90 degree. Okay. When theta is equal, when this theta is equal to 90 degree, now you have to move this theta. So as we go on moving this theta, sorry, let me rub it off. Fine. So now we say that this theta is 90. When this theta will be 90? When we completely rotate it. When we rotate this theta like this, okay? So at that time, your n vector will be like this, and your force vector will be like this. When force vector and the area vector are perpendicular to each other, the case becomes like this. The case is like this. Sorry. We have the case like this. Okay. So we have an area like this. First of all, we have to draw the area vector. We know the direction of the area vector will be in this direction. This will be the direction of our area vector. N cap represents our area vector. Fine. And our force has to be in this direction. F vector. This direction represents our area vector. When the direction between force and area is 90, when the angle between force vector and area vector is 90. Fine. Let's talk about sigma. How much will be the normal stress in this case? The normal stress in this case is, now theta is 90. So this is 90. Look into this formula. Sorry. We have it here. So theta is 90. 90 into 2 is 180. Cos 180 is minus 1. Minus 1 plus 1 is 0. Therefore, sigma becomes equal 0. Fine. And how much will be shear stress? Okay. So as far as the shear stress is concerned, for theta equal to 90, so it will be, we have to make a little modification here.